Welcome to the deep dive. Today we're getting into something, well, truly mind-bending. The Skyhook.
Yeah.
Think of it maybe as a shortcut to space. We're exploring this idea, what if you could just hook payloads right into orbit?
It's a really fascinating concept. Fundamentally, a skyhook is a proposed type of momentum exchange tether.
Okay, momentum exchange, like a swap.
Exactly. Picture a heavy orbiting station. It's got this long cable, a tether, hanging down towards the upper atmosphere. A payload, launched on a smaller rocket just partway up, meets the end of this swinging tether.
It catches it.
It hooks on, yes. And then the rotation of the station and tether essentially flings the payload the rest of the way into orbit. The station gives up a little bit of its energy, its momentum,
Right.
which it then has to regain, maybe with gentle thrusting.
Right, so it's using the station's orbital energy. And that's the key mission here, isn't it? To massively cut the cost of getting things, especially to low Earth orbit.
Precisely. LEO is where so much happens. Satellites, the ISS, making access cheaper is, well, it's crucial.
And important to stress, this isn't like that classic sci-fi space elevator going all the way down to the surface.
No, not at all. It's much shorter, orbiting hundreds of kilometers up. It never touches the ground. You still need a launch vehicle to get the payload up to meet the hook.
Okay, but here's where, for me, it gets really clever. The rotating skyhook idea.
Yeah.
Can you unpack that? It sounds like orbital gymnastics.
It really is ingenious. So you rotate the tether around the main station, but opposite to the direction the station itself is orbiting the Earth.
Opposite? Why?
Well, by timing it just right, the tip of the tether, the hook, can actually have a very low or even zero velocity relative to the ground when it reaches its lowest point. From the ground, it might look like it just sort of drops down almost vertically, pauses, and then goes back up.
Wow, so it makes the rendezvous much simpler.
Much simpler. And critically, it massively reduces the aerodynamic stress, the drag on the tether tip. This means it can dip lower into the atmosphere to grab the payload, and the payload doesn't need to be going nearly as fast.
That seems like a huge advantage over just raw rocket power.
It absolutely is. It sidesteps a lot of the tyranny of the rocket equation for that final orbital insertion.
Now, this sounds incredibly futuristic, almost like something out of, I don't know, the next century. But people have been thinking about this for a while, haven't they?
Oh, yes. Decades, actually. You had proposals from Isaacs back in 1966, Moravec in 1976. Real visionary thinking, considering where spaceflight was back then.
Just after the moon landing, basically. Amazing.
And we have actually flown tether experiments, though not a full skyhook. NASA's TSS-1R mission on the shuttle in '96 deployed almost 20 kilometers of tether.
Didn't that one snap?
It did, unfortunately, but we learned a huge amount from it about tether dynamics. Then there was YOES-2, the young engineer satellite in 2007. That one successfully deployed nearly 32 kilometers of tether, a world record, actually. So the basic tech has been tested in space.
Okay, so concept history, some experiments, but let's talk brass tacks. Engineering reality. Boeing looked into this for NASA, right? The Hastol study.
Yes, the Hypersonic Airplane Space Tether Orbital Launch System study, Hastol, around 2000-2001, and they came back with something quite striking.
Which was?
Basically, they concluded you don't need unobtainium. Their report said, and I'm paraphrasing slightly, we don't need magic materials like Buckminster fullerene nanotubes. Existing materials will do.
Whoa, hold on. So the big blocker wasn't finding some super material.
According to Hastol, no. The challenge shifted, you could say, from fundamental material science to, well, massive scale engineering and operations, but doable with known materials.
That is a huge shift. What kind of scale were they talking about then, using existing stuff?
They proposed a 600-kilometer long tether, orbiting around 700 kilometers up near the equator, made of things like Spectra 2000 or Xylon PBO materials we already have, rotating quite fast, a tip speed of about 3.5 kilometers per second.
600 kilometers. And the mass.
The tether alone was estimated at around 1,300 tons to lift a payload of about 14 tons.
1,300 tons. That's immense, like naval destroyer sort of weight.
Yeah.
And you still needed a hypersonic plane.
Yes, the concept involved a hypersonic vehicle intercepting the tether tip at Mach 10, way up at 100 kilometers altitude, so still very challenging.
So not exactly simple then, even with existing materials. Did they flag other issues?
They did, particularly in Phase 2 of the study. While they said there were no, quote, fundamental technical showstoppers, there were definite hurdles. A big one was the concern about atomic oxygen erosion on materials like Spectra 2000 at those altitudes.
Atomic oxygen.
Yes, single oxygen atoms up there are very reactive and can degrade materials over time, so you'd need better materials or coatings or ways to mitigate that. Substantial improvements needed, even if the basics worked.
Okay, so summing this up, the Skyhook is this incredibly clever physics concept using momentum exchange and rotation to potentially slash launch costs.
Right. It's elegant physics meets massive complex engineering.
But Hastol showed, maybe surprisingly, that it might not require undiscovered miracle materials, just very advanced engineering with what we have, plus solving issues like material degradation.
Exactly. The path isn't blocked by unknown science, perhaps, but by known, very difficult engineering challenges.
So let's leave our listeners with this. If
Yeah.
we could overcome those challenges, if a Skyhook or something like it made getting to orbit, say, as routine as flying across the ocean,
Mm-hmm.
what does that future look like? How does that change everything science, using space resources, maybe even humanity's place beyond Earth?
That's the profound question, isn't it? If that barrier truly falls, what kind of future does it unlock for all of us?
Something fascinating to think about. Thank you for joining us on this deep dive into the Skyhook concept. We hope you found it as intriguing as we do.